This lesson is over parts of 6.3 and 6.4 from the textbook. We're not doing all of them because in the book they do derivatives and integrals of these functions all together. We are only doing derivatives, but I still would recommend you look at the book if you have more questions or want to see more examples, okay? But what we're going to do is we're going to talk about how to find the derivatives of a handful of different transcendental functions. Transcendental means like log functions or exponential functions or trig inverse functions, and today we're looking specifically at exponentials and logs. Now we already have the derivative for one log formula, okay, and I'm going to go ahead and write that up here as a refresher. We know that the derivative of the natural log of u, now I'm writing it with u because this could be a composition, okay, composition of functions when we have something inside the other one. And that derivative is equal to 1 over u times u prime, or in other words, 1 over u times du over dx if you want to write it with the Leibniz notation. Either of these are fine. I usually tend towards this one, but you can use whichever one you want. The idea, though, is that when we take the derivative of the natural log, okay, it's going to be 1 over whatever is inside the log, and then we multiply by the derivative of the inside. Okay, so in the case of natural log x, the derivative is 1 over x. We don't need to multiply by the derivative of x because that's just 1. But if I were taking the derivative of natural log of, let's say, sine x, then my derivative would be 1 over sine x times the derivative of sine, which is cosine. Okay, so we still need to use the chain rule, and in fact, chain rule is going to show up in most of the functions that we do from here on out, okay? All right, the other thing that I want to make sure that you are really good on, so if not, you should probably stop this and go back and watch the other videos, is implicit differentiation, specifically logarithmic differentiation, because we are going to use those processes for developing our formulas for these derivatives, okay? All right, so I've got 4 formulas here that I'm trying to develop. For each of these, u represents a function in terms of x. Okay, we'll use that when we have a composition. And then a and b are both elements of the positive real numbers. So a and b are constants. Okay? Where u is a variable expression. So u could be sine x, it could be x squared minus 12, but it's some function of x. All right, so looking at this first one, we want to take the derivative of e to the x. Because we do not have a formula yet, we are going to rewrite the function y equals e to the x logarithmically and then take the derivative, okay? Oh, also, if you are not familiar with log properties yet, you absolutely need to refresh on those, okay? Because we're going to use several of them. There's a lot of things that I'll do here that might not make sense if you don't remember log properties, okay? So there's a PDF in the Schoology in the Unit 2 folder that says keys and extra practice, and it says review of logs. There are also some log assignment or log practice problems that you can do in Delta Math optionally, okay? All right, so what I'm going to do is I'm going to write that function as y equals e to the x, and then my first step will be to take the natural log of both sides of this equation. So I'll have natural log, I'm not using an equal sign because it's not equal, but I'm just rewriting. So natural log of y is equal to the natural log of e to the x, and the natural log of e to the x is equal to x. So I have that the natural log of y is equal to x. Now what I'm going to do is I'm going to take the derivative with respect to x of this equation. So derivative with respect to x of this whole thing. So I'm taking the derivative implicitly. Make this a little bit bigger. Okay, and so that's going to give me, over here, that's going to give me 1 over y times y prime is equal to, and then the derivative of x is just 1. Okay, so then solving for y prime, I get that y prime multiplied by y is equal to y, which, because the function was defined explicitly to begin with, I'm going to go back to that, is equal to e to the x. So what I have done is I have developed a formula for the derivative of e to the x, and I found that the derivative of e to the x is equal to itself. Okay, so the derivative of e to the x is e to the x. From here on out, I do not need to use logarithmic differentiation. If e to the x shows up in a problem and I'm differentiating, I know that it is its own derivative, okay, because now I have that formula. All right, this next one is a little bit different, but pretty similar. The difference is that here we just have e to the one single x. Here we have e to an expression in terms of x, okay? In other words, what we need here is the chain rule because this is a composition of functions, okay? I'm still going to go ahead and write that out. So we have y equals e to the u, and then we take the natural log of this equation, and we get the natural log of y is equal to, and then the natural log of e to the u is u, okay? Next, taking the derivative with respect to x of this whole thing, I get that, I get 1 over y times y prime is equal to, and then the derivative of u, okay, the derivative of 1u is 1 times u prime, or you could write du over dx if you want to. All right, so then solving for y prime, I get that y prime is multiplying by y is equal to y times u prime. And what was y? Y was e to the u. So e to the u times u prime. Okay? My derivative of e to the u is itself, but then we have to multiply by the derivative of the inside function. Okay, so I'll give you a quick example. If we're taking the derivative of e to the 5x cubed, okay, according to this, my u is 5x cubed, all right? U prime would be 15x squared, so my derivative is e to the 5x cubed times 15, where's the one? There we go, 15x squared, all right? So that's how chain rule works with exponentials. Okay, next one, again, expanding a little bit more. Here, we have an exponential function again, but instead of a base of e, we have a base of a, all right? A is any constant, any positive constant, okay? And u is still an expression in terms of x. So, writing my function in logarithmically here, okay? So we start with y equals a to the u, and then we take the natural log of the whole thing, so we get the natural log of y is equal to the natural log of a to the u, okay? And then we're going to use the log property to take this u and move it down here and multiply it in front. That is not a calculus step. That is all algebra. There's an algebra property of logs that says if I have the log of something to a power, I can take that power and move it to the front as a coefficient, okay? And so that's what I've done. That's the reason we're doing logarithmic differentiation, is because we want to move that variable expression u down from out of the exponent. So the natural log of y is equal to u times the natural log of a. Okay, now we're going to take the derivative with respect to x of this whole thing. And so on the left side, once again, we have 1 over y times y prime. On the right side, we have u times natural log of a that we're taking the derivative of. And here is the thing that you might be thinking. You might be thinking that we need to use the product rule. In this case, we do not, because if you remember, a is a constant, and the natural log of a constant is still a constant. So imagine that a is a 5. The natural log of 5 is a constant, meaning that it operates as a coefficient. So when I'm taking the derivative of u times natural log of a, I can just keep natural log of a as a coefficient and then worry about the derivative of the other part. Okay? If you want to use the product rule, that's fine, but the derivative of natural log of a is 0, so half of your derivative should disappear. Okay? All right, so then I still need to take the derivative of the u part, so I'm just going to write that as u prime. Okay, and then to solve for y prime, multiply both sides by y, and we get y equals the natural log of a times a to the u, which is y. Okay, y was a to the u, so I'm multiplying by, and I'm going to put it in the middle, multiplying by the original function, and then times u prime. Okay, so that is my derivative of a to the u, natural log of a times a to the u times u prime. okay? Now, you might notice that this looks similar to the last one, okay? Two major differences. The first difference is that we have a different letter as our base. E is the constant. It is defined as a log of the natural base. It can be defined with a limit, but it's 2.71828 blah, 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 but it is a constant, okay? It's just like having a 3 there, all right? The difference here is that we can have any positive constant as our base, okay? But when we take the derivative of something that does not have e as the base, we also need to multiply by this extra natural log a as a coefficient. All right. Now, if you think about the other one, if we use this formula to take the derivative of e to the u, we would have an extra natural log of the base in front of this, okay? But the natural log of e is equal to 1, so it would just cancel itself out anyway. All right? So essentially it's the same formula, but this one is more inclusive to allow us to have derivatives of things that are not equal to e. All right. And we're going to do some more examples in a minute, but let's do one more formula first, okay? So here we're taking the derivative with respect to x of log base b of u. Again, b is a constant, okay? B is a positive constant. It is the base of the log, and then u is an expression in terms of x. So we have a composition of functions where u is the inside function. All right. Here we do not have to take the derivative logarithmically, but what we are going to do instead is we are going to use the change of base formula to rewrite this as a log that is in base e, or we're going to write it as a natural log. Instead of having a separate formula for the derivative of a log function in every base, we only need to know how to take the derivative of a log that is in base e, so in other words, natural log, and then everything else can be changed to be a natural log. So, review on change of base formula. Okay, so the change of base formula says log base b of u is equal to the natural log of u, because I'm choosing to be base e, so natural log of u over natural log of b. Okay, to help me remember which direction these go in, I remember that b, the base, goes on the bottom. So whatever number is down here goes right here. Okay? All right, so once we have rewritten this, now we can take the derivative using the formulas we've used before. There's one thing that I want to point out here, though. Even though we have a fraction, we do not have to use the quotient rule, because just as natural log of a up here was a constant and operated as a coefficient, natural log of b is also a constant. So another way to look at this is 1 over natural log b as a coefficient times the natural log of u. Okay, and now that's the same thing as, okay, well, I want to take the derivative of, let's say I want to take the derivative of 5 natural log of cosine x. Okay, well, if I'm taking the derivative of this, the 5 just stays in front as a coefficient, all right? And then the derivative of that would be 1 over cosine times the derivative of cosine, which is negative sign, and then we could kind of move some things together and make one fraction out of it. All right, but the idea is the 1 over natural log b does not require a product or a quotient rule. It operates as a coefficient. Okay, now if we want to write a formula for that derivative, if you prefer to think about it, if you'd rather memorize a new formula instead of just remembering to change the base, okay, this is what happens there. So we're looking for the derivative with respect to x of the natural log of u over the natural log of b. And 1 over natural log b is a coefficient. So 1 over natural log b stays there. And then using the same formula that we used up here, the derivative of natural log u is 1 over u times u prime. Okay? So if you want to memorize that formula, that's fine. It's going to be 1 over natural log b times 1 over u times u prime. But again, I think it's easier just to say, well, let's change it out of base whatever and into base e. Okay, and I'm going to do the examples in another video.